right, good morning, everybody at home. Can I get a thumbs up that you hear me and see the board okay? All right, here we go, guys. This is, for this section, the last inverse trig function. However, the next section, we'll talk about the inverse reciprocals. So we have the inverse tangent left. So hopefully, like I said, after seeing inverse sine and inverse cosine, this goes a little bit smoother when we keep adding more inverses. So guys, just to kind of bring us back what we already know. As far as the inverse sine is concerned, the inverse sine is only capable of spitting out angles. Oh, guys, I'm doing cosine from yesterday. Is only capable of spitting out angles between pi over 2 and negative pi over 2. Those are the only angles that survived the cut of its graph, right? He goes from pi over 2 to negative pi over 2. Right, then we have the inverse cosine. We saw yesterday that the inverse cosine is only going to be capable of spitting out angles from 0 to pi. Quadrant 1 and quadrant 2 angles. Then I gave you the little cheat chart where I already spoiled for you the fact that no inverse trig functions are capable of spitting out quadrant 3 angles. Quadrant 3 angles do not survive the cut of any of their graphs. So right now we know if you take the inverse sine of a positive ratio, it's going to spit out a quadrant 1 angle between 0 and pi over 2. If you take the inverse sine of a negative ratio between 0 and negative 1, it's going to spit out a quadrant 4 angle between 0 and negative pi over 2. And then the cosine, if you take the inverse cosine of a positive ratio between 0 and 1, it's going to spit out a quadrant 1 angle between 0 and pi over 2. And then if you take the inverse cosine of a negative ratio between 0 and negative 1, it's going to spit out an angle in quadrant 2 between pi over 2 and pi. All right, so now we have to figure out what is tangent going to do. How does the tangent create the inverse tangent? Because yet again, the tangent graph is not a one-to-one function. It is not going to pass the HLT. We have to cut a portion of its graph to force his inverse to exist. All right, so let's go down here. So here's the graph of tangent. Can I put it all on? All right.
Sorry, it's the far right.
Right. All right, so guys, as far as the tangent is concerned, the tangent, when you go to plug an angle in and then it spits a ratio out, there were lots of bad angles. There were angles that you got undefined outputs for that created these vertical asymptotes. So as far as the tangent's domain was, x wasn't allowed to be pi over 2, or 3 pi over 2, or 5 pi over 2, or negative pi over 2. All these odd integer multiples of pi over 2 were bad guys. So his domain was x cannot be pi over 2 plus or minus every pi radians in either direction created another bad guy. So pi times k revolutions was his domain. But then as far as the ratios that he spit out, guys, look at the ratios. You plug this angle in, that ratio comes out. You plug this angle in, that ratio. This angle, that ratio. The ratios were endless. They went off to infinity and negative infinity. So there's no ratio that can't come out of the tangent function. Okay? All right, well, guys, does this graph have an inverse? Is this a one-to-one function that passes the HLT? No. So where can we cut it to make the inverse exist? So, guys, the tangent function is kind of nice because he's individual curves that repeat. So basically, to make his inverse exist, we just keep his first curve. As long as we keep that first cycle, that first period, this entire cycle passes the HLT. So we're going to keep his first cycle to make the inverse exist. So that means we're going to cut it at negative pi over 2 and pi over 2 and keep this entire first curve as his portion that we keep for his inverse. All right, so we know it doesn't exist, but if we restrict it from negative pi over 2 to pi over 2, we got ourselves an inverse that can exist. So guys, that's why the inverse cosine or inverse tangent is only going to be capable of spitting out angles between negative pi over 2 and pi over 2, because those are the only angles that survived the cut of his graph. Quadrant 1 angles and quadrant 4 angles. I think I had that written down here, yeah. Quadrant 1. So guys, he behaves just like the inverse sine. He is capable of spitting out the exact same angles as the inverse sine function, okay? All right, let me move mine up. Actually, I'm going to do this. If you guys recognize this is a ratio of 1, this is a ratio of 1, when pi over 4 went in, because remember, the tangent repeated quicker, so we actually counted by pi's over 4, not pi's over 2. When pi over 4 went in, a 1 came out. When negative pi over 4 went in, a negative 1 came out. I'm just trying to keep points to create his inverse graph. So we have the point 0, 0. We have the point pi over 4 went in and a ratio of 1 came out. We have negative pi over 4 went in and a ratio of negative 1 came out. And then technically, when pi over 2, he created that undefined. You couldn't even plug him in, all right? But keep that in mind. All right, now we'll be able to create his inverse. All right.
You can erase this top right now, I'm sorry.
Don't erase that? Oh, now, okay, yeah.
Yeah.
All right, so guys, for the inverse tangent, remember, you would have taken the tangent function, y equals the tangent of x, switch your x and y. That's the implicit version of the inverse, right? It's not in the correct form. We want it to be in y equals form. So we'll get it in the explicit form by solving it for y. So we have to take the inverse tangent of each side. And then we get y equals the inverse tangent of x. So now you plug a ratio in, and it's going to spit out an angle. Okay, so guys, if you think about this, the point 0, 0 was on the graph of his inverse, which means now you have ratios, 1, 2, -1, -2 going in, and you have angles coming out, right? So it went from pi over 2 to negative pi over 2 that survived, and then I gave you some pi's over 4, halfway in the middle. All right, so 0, 0 used to be on the graph of tangent. Well, you split the x and y, 0, 0 is still on the graph of the inverse. If pi over 4, 1 was on the graph of the original, well now, when a ratio of 1 goes in, it spits out an angle of pi over 4. Now, if negative pi over 4, -1 was on the original graph, now you plug a ratio of -1 in, and it spits out an angle of negative pi over 4. And then before, you used to have an x-coordinate at pi over 2 that was undefined. Now you have an undefined value at a y value of pi over 2. So guys, the angle pi over 2 is not physically going to be able to come out of this function. It really didn't survive the cut because if you remember, on tangent's graph, it was an asymptote. So it's not really an angle it's going to be capable of spitting out, but we can go right up onto pi over 2. And the same thing here. Negative pi over 2 used to be a bad angle that couldn't go into the tangent. So now it's an angle that the inverse is incapable of spitting out. So we're going to have an HA, a horizontal asymptote, at negative pi over 2. Right, and then as you plug ratios in, angles approaching pi over 2 come out. As you plug negative ratios in, angles approaching negative pi over 2 come out. So the graph looks like this. It doesn't go past them. It's sandwiched in the middle of angles between negative pi over 2 and positive pi over 2. So now the domain of the inverse tangent, guys, go ahead. Plug any ratio you want in, because all those ratios survived the cut, and they were endless. The ratios went from negative infinity to positive infinity. So now you have endless ratios that you're allowed to plug into the inverse tangent. Right, those are ratios, go in as x, but now the angles it's capable of spitting out are sandwiched in the middle of negative pi over 2 and pi over 2. But they don't include negative pi over 2 and pi over 2. So you can't actually get those angles out. It just goes right up into them. So you can't include them like we could include them on the other inverses. Okay? So look at what the graph is showing us. If I plug a ratio greater than 0 in, an angle between 0 and pi over 2 comes out. That's a quadrant 1 angle. Okay? So if you had to put a triangle or create an angle, you'd want to put that angle in quadrant 1. Because when you take the inverse tangent of a positive ratio, it's coming out as a quadrant 1 angle. All right, if I plug a ratio less than 0 in, if I plug any of these ratios in, an angle between 0 and negative pi over 2 is going to come out of that function. And those are quadrant 4 angles. So you'd want to put your triangle or put your angle in quadrant 4. Okay? So again, it's going to feel a lot like the inverse sine. All right, ready to do some problems? Let's put this to good use. Let me give you a second to finish that. You know what? I'm going to get, when I move this up, I feel like I didn't have room at the top of our notes, guys, but if you want to put this here, I'm going to redraw it in a second, but you might have room to put it here. So as far as the all students take calculus, right? Now we're talking about the tangent function. So all trig functions got you a positive ratio for angles in quadrant 1. And then the tangent didn't get you a positive ratio for an angle, again, until quadrant 3. So that means if it's only going to be capable of spitting out quadrant 1 and quadrant 4 angles, it's not capable of spitting out this quadrant 3 angle, which means you're going to want to convert it. If you ever are left with a quadrant 3 angle, you're going to want to convert it to a quadrant 1 angle that gets you the exact same ratio. There is an angle in quadrant 1 and quadrant 3 that get you the same tangent ratio. All right, well, that means the tangent function got you a negative ratio for angles in quadrant 2, and it got you a negative ratio for angles in quadrant 4. Well, remember, the inverse tangent is only capable of spitting out angles in quadrant 4. So if you're left with a quadrant 2 angle, you're going to have to convert that to a quadrant 4 angle that gets you the exact same ratio. Okay? All right, now we should be good to go. I'm going to leave it up for a few seconds. Let's get ourselves ready. We might want some triangles in case we don't remember our ratios by heart. Is that on the screen? Yeah. All right, here we go. They asked us to find the exact value of the inverse tangent of 1. Well, guys, remember, the inverse tangent, you plug a ratio in, we know the answer to this is an angle. He's only capable of spitting out angles between quadrant 1 and quadrant 4. All right, so you have to figure out the tangent of what angle equaled a ratio of 1. Well, guys, if you remember, as far as your unit circle is concerned, these are the points that survived the cut. Tangent was the y-coordinate over the x-coordinate. So you start throwing zeros over ones, you're either going to get 0 or undefined. So it's definitely not one of your quadrantals that had a ratio of 1. So that leaves your multiples of 30, 60, and 45 to actually end up with a tangent ratio of 1. Do you remember which tangent, what angle had a tangent of 1? It was our 45 degrees. He had a tangent of 1, which means it's a pi over 4, and it had to land in quadrant 1 if the ratio was positive. So what multiple of pi over 4 landed in quadrant 1? Pi over 4. The answer to this question is pi over 4. It's a 45-degree angle. All right, look at the next one. The inverse tangent of negative root 3. Well, guys, we know if you take the inverse tangent of a negative ratio, it should spit out a quadrant 2 angle. All right, so we are working here. We can go a quadrant 2, guys. What am I doing? Quadrant 4 angle. I can't get cosine out of my mind. All right, so if it's a quadrant 4 angle, we know it's somewhere down here, somewhere between 0 and negative pi over 2. Now you got to figure out which angle was it? Which special angle, pi over 6, pi over 4, pi over 3, who had a tangent ratio of negative root 3? Anybody know which one had a tangent ratio of root 3? Was it 45, which we just said was 1, so he's out? Was it 30 or 60? Well, guys, the tangent of a 30 is 1 over root 3, O over A. And then that would be what, root 3 over 3 when you rationalize it? So it ain't a 30. What's the tangent of a 60? Root 3 over 1. It's a 60, which is pi over 3. And since it's in quadrant 4, it's not positive pi over 3, it must be negative pi over 3. And that's the angle that the inverse tangent would be capable of spitting out. All right? All right, what about the next one? How's the inverse tangent of root 3 over 3? Well, guys, we know if we take the inverse tangent of root 3 over 3, a positive ratio, it's going to spit out a quadrant 1 angle. The answer to this is a quadrant 1 angle. All right, so if he's capable of those two quadrants, we've already determined it's got to be a quadrant 1 angle. So now you got to figure out, well, a tangent of what special angle gave you a ratio of root 3 over 3? The tangent of what angle gave us root 3 over 3 as a ratio? Because I just said it. It's definitely not 45, the tangent's 1. It's definitely not 60, the tangent's root 3. So that leaves what other special angle for it to be? A 30, which is pi over, and since he's in quadrant 1, he has to be positive pi over 6. All right. So now if they ask you to take the inverse tangent of 0, well, remember, to have a ratio of 0, it's kind of like, well, how did we get O over A and all that to be 0? Well, we didn't. Our quadrantals, though, when we redefined the trig ratios as y-coordinates over radiuses and y-coordinates over x's, then you could have a tangent of 0 as your ratio. All right? So think your quadrantals. We know the inverse tangent of a ratio, the answer is definitely an angle, right? So if he's capable of spitting out angles from pi over 2 to negative pi over 2, think about what quadrantal angles that is. That's the angle right here, 0 radians at the point 1, 0. That's pi over 2 at 0, 1. And then this is negative pi over 2 at 0, negative 1. The tangent was the y-coordinate over the x-coordinate, right? We're trying to figure out the tangent of what angle had a ratio of 0. So it has to be one of these quadrantals. Whose y-coordinate over their x-coordinate equals 0? Only an angle at how many radians? 0. You put this over that, 1 over 0, it's undefined. You put negative 1 over 0, it's undefined. So they don't have a tangent ratio of 0. But at 0 radians, or 2 pi, but remember 2 pi would never come out, doesn't survive the cut. It's 0 over 1 is 0. It's got to be 0 radians right there at that angle. Okay? Go ahead.
Question.
Go ahead, Jay.
On B,
Yep.
why do we use negative pi over 3 instead of using 5 pi over 3?
Is 5 pi over 3 an angle between pi over 2 and negative pi over 2? See, it's kind of like Jay. If you wanted to get to 5 pi over 3, 5 pi over 3 definitely has a tangent ratio of negative root 3. The problem is 5 pi over 3 is not an angle he's capable of spitting out. Think about how you had to get to 5 pi over 3. You had to start here, and you had to rotate all the way to there. There's 5 pi over 3. None of these angles survived the cut of the tangent's graph. The only angles he's capable of spitting out are from pi over 2 to negative pi over 2. So you can say 5 pi over 3 is true if maybe we were solving an equation. The problem is it's not an angle the inverse tangent can spit out. So you have to find the same, well, not the same angle. You have to find an angle that lands in the same spot as 5 pi over 3 that gives you the same ratio, negative root 3, but he's an angle between pi over 2 and negative pi over 2.
Okay.
Okay? I'm not saying 5 pi over 3 doesn't have that tangent ratio. He's just not an angle that survived the cut from pi over 2 to negative pi over 2. Okay? All right. All right, let's go down here. Let's do some compositions now. All right, let's say we take the inverse tangent of the tangent of pi over 10. Well, guys, you take the tangent of a angle. The answer is a ratio. You take the inverse tangent of a ratio, and the answer has to be an angle, but not any angle. It's got to be an angle between pi over 2 and negative pi over 2. So as long as pi over 10 lands in quadrant 1 or quadrant 4, in between pi over 2 and negative pi over 2, we got ourselves a keeper. Because the inverse tangent and the tangent should cancel, and we're left with that angle. Well, guys, in the world of pi over 10, 10 of them get you to there. Half of that would be 5 pi's over 10. So 1 pi over 10 definitely lands somewhere over there in quadrant 1. That's a beautiful angle. It's an angle he is capable of spitting out. He's our answer. All right. Let's look at the next one. The inverse tangent of the tangent of 4 pi over, I'm pretty sure it says 5. I got a squiggly line through it. Is that 5?
Yeah.
Okay. All right. Well, guys, you take the tangent of an angle. The answer is a ratio. You take the inverse tangent of a ratio, you got yourselves an angle. The angle is definitely the answer to this problem. The problem is when the tangent and inverse tangent cancel, is that an angle that the inverse tangent is capable of spitting out? Well, the inverse tangent can spit out angles between pi over 2 and negative pi over 2. Where does 4 pi over 5 land? Well, in quadrant 2, right? Here's your 5 pi's over 5. Cut 5 in half, which means 2.5 pi's over 5 land right there. 4 pi over 5 definitely lands in quadrant 2. That is not an angle that he would be capable of spitting out. So we got to convert it, right? So let's get our reference angle. If this is 4 pi over 5 and this is 5 pi over 5, what's the reference angle? How many pi's over 5 live in between 5 and 4? 1 pi over 5. So our reference angle is pi over 5. So we're going to have to use that when we go to convert it. Well, guys, remember, all students take calculus. Tangent was positive here, and the tangent ratio was positive there. It was negative for angles in quadrant 2, and it was negative for angles in quadrant 4. So if we're working with a quadrant 2 angle right now, he can't spit that out. But there's an angle in quadrant 4 that got you the exact same negative ratio. So we got to figure out what angle is that in quadrant 4. All right, so do this. If you have a reference angle of pi over 5, give yourself an angle in quadrant 4 that also has a reference angle of pi over 5. And the reference angle is always in between your angle and the x-axis. So guys, does anybody know what angle has a reference angle in quadrant 4 of pi over 5 between 0 and negative pi over 2? Not pi over 5, but negative pi. Michael, negative pi over 5 is what he would be capable of spitting out. Okay? All right, what about this one? The inverse tangent of the tangent of negative 7 pi over 6. Well, you take the tangent of an angle, the answer is a ratio. You take the inverse tangent of a ratio, you got yourselves an angle. So the angle should be our answer as long as it is an angle that this function is capable of spitting out. So they should cancel, and we should be left with negative 7 pi over 6. Well, what do we got? He can spit out angles between pi over 2 and negative pi over 2. Where does negative 7 pi's over 6 land? Anybody know? In quadrant 2 again, right? So now we went all the way to here. Here's negative 6 pi's over 6, right? So now you're going to have, here's your negative 7 pi over 6. What's the reference angle in between them? How many pi's over 6 live in between negative 6 and negative 7? Just 1. Negative pi over 6. Remember, your reference angle is never negative. It's just 1 pi over 6. So yet again, if you have an angle that landed in quadrant 2 that this is incapable of spitting out, you'd have to convert it into that quadrant 4 angle that is an angle he would be capable of spitting out that gets you the exact same ratio as the angle in quadrant 2. So guys, yet again, we're going to convert it to quadrant 4. So take your reference of pi over 6. Give yourself a reference of pi over 6 in quadrant 4. So what angle has a reference angle of pi over 6 in quadrant 4 between 0 and negative pi over 2? Negative pi over 6. And you're done. Yes?
Wouldn't it be a positive pi over 5 since we're working with a positive ratio, not a negative?
No, because if you were an angle in quadrant 4 between 0 and negative pi over 2, would you be a negative or positive angle? You'd have to be a negative. So the thing is, when you have a quadrant 2 angle, we're converting him to a quadrant 4 angle in between 0 and negative pi over 2. So even if this one's positive, when you convert him to the quadrant 4, you're converting him to an angle between 0 and negative pi over 2. Okay? All right, so those are the hard ones. These are the best ones. So look at these ones. Now we do the composition the other way. Now you're taking the tangent of the inverse tangent of 4. Well, guys, you take the inverse tangent of a ratio, you get yourself an angle. You take the tangent of an angle, and the answer is definitely a ratio. But guys, if you remember, there were no bad angles that went into tangent, which means there are no bad ratios that you could plug into the inverse tangent. So whatever ratio you are left, there's no bad ratios. It's O over A, it's Y over X. There's nothing that's going to say they have to be between 0 and negative 1 or 0 and 1. There's no bad ratio for tangents. There should be no problem that they could give you in this reverse order where you'd be left with a bad answer. So the tangent and the inverse tangent cancel, you're left with a ratio of 4, which is a good guy. There's no bad ratios. They went from infinity to negative infinity. All right, you take the inverse tangent of a ratio, the answer is an angle. You take the tangent of an angle, and the answer is definitely a ratio. And there's no bad ratios. So when the tangent and the inverse tangent cancel, and you're left with a ratio of negative 10, great. There can't be a bad ratio. So those ones were awesome. All right? All right, so we've seen all the inverses. Now I've given you a homework on inverse tangent. So they're pretty quick problems. So this one, I know I made yesterday's inverse cosine problems, guys. I made them due tonight, I think, actually. If that's a problem for anybody, guys, I do not mind pushing it back. Just let me know. So when I assigned this homework, there's no rush. I didn't make this one due, guys, until the Monday night of our 3-day weekend. But the homework that I assign tomorrow is also going to be assigned due for Monday of that weekend. So they'll both be due Monday night, but you have the next few days to get these done. We have one more thing to go over in section 1, and then we're done with section 1, and we'll do that tomorrow. Okay? Is everybody good? All right, let me double check the attendance at home, and then you guys will be good to go.